Hello, I am John Ullman, and this creature behind me is Cranberry, who might make an appearance from time to time. It's a nice snowy day in Brookline to be sitting here recording this video. This is going to be lecture 2 in our course, and the subject is Reconstruction attacks. This is the first of 2 lectures on Reconstruction attacks. And what this section is really all about are the ways that releasing simple aggregate statistical information about a data set can compromise the privacy of individuals. So it might seem intuitive that releasing statistics like the average age of all those in the data set who are male is a harmless thing to release. But what we'll see is that releasing lots of these statistics, even very noisy versions of lots of these statistics, can reveal a lot of information about specific individuals in the data set. And what we're going to do is build up to models where we can show that reconstruction is not only something that might happen, but actually it's going to be inevitable if we release too much information about the data set. And this is going to kind of inform and motivate what we're going to see in the next unit, where we introduce differential privacy as a method for preventing reconstruction attacks and a host of other privacy issues. So what I'm going to do is start out with some kind of concrete examples of reconstruction attacks to introduce the idea. So we'll focus on something called differencing attacks, and then a slightly more complicated example of the reconstruction paradigm. And then we'll go into a theoretical framework called linear reconstruction attacks that's going to let us prove interesting things about when reconstruction is possible and how it can be done. So we'll start by talking about some examples of what really are aggregate statistics and when our intuitions about aggregate statistics might break down. So let me get my trusty iPad pen out and we can start. So I'll start out describing sort of a simple model of how aggregate information can reveal a lot about individuals, which is differencing attacks. And before that, I'm just going to talk about the simplest possible example of releasing a count. So let's suppose that you've started a new job and you signed up for health insurance provided by your employer. And the insurance company makes certain aggregate statistics available to your employer, for example, so that they can project costs into the future. So they let you ask, questions such as how many employees were born on July 18th, 1983, and live in the zip code 98152, and have agoraphobia, which is a medical condition characterized by fear or an anxiety response to crowded or unsafe spaces. Okay, so let's suppose the answer they get to this query is that the number of such employees is 1. Well, even though this query seems like it's an aggregate query, it's asking for a count of how many employees at the company have some property, not asking about any specific employee, I think it's pretty clear that an employer who knows your home address and birth date can now discover that you have agoraphobia. And if you're not totally convinced by this example, maybe you work at a very large company where there are multiple people with your birth date and zip code, you can imagine adding a few extra attributes like your start date at the company or your specific job title. This is meant to be sort of an example, but it shows that even questions that don't pertain directly to individuals can reveal a lot about individuals. And maybe you think this example's a little too obvious, right? The answer to the question was 1. There's only 1 such individual, so we're not really aggregating anything. And maybe these problems would entirely go away if we did something simple like replace exact answers to these questions with approximate answers, like there are less than 5 such individuals. So maybe we just don't answer questions if the answer is too small. We say, sorry, the answer is too small. So differencing attacks show that small answers aren't really the issue. So even aggregate statistics that seem to have successfully aggregated a lot of people's data together can single out individuals because the difference between 2 queries, both of whose answer is large, might actually winnow down to a specific person. Okay, so this is what a difference attack is. And an example of a difference attack is the following pair of queries. So Q1 is going to be how many employees joined before, let's say, your start date is September 20th, 2020. So this is your start date. And suffer from agoraphobia. And question 2 is how many employees joined before 09/21/2020, which is your start date plus 1, and suffer from agoraphobia. So these are 2 questions, each of which seem fairly general. They don't look very specific. And suppose the answer is 417 to the first question and 418 to the second question. So both of these questions are aggregating lots of people together. They're not singling out any one individual. But an employer who knows that you began on September 20th, 2020, now knows that one of the employees who started on that date has agoraphobia, because sometime on September 20th, the number of employees who suffer from agoraphobia increased from 417 to 418. So if you, for example, are the only person who started at the company on that date, it's now known that you suffer from agoraphobia. And again, this is meant to be an example. Maybe multiple people started on that date, in which case the employer learns that one of them has agoraphobia. Maybe they can combine with some additional information about you and figure out that it was you specifically. Okay, so a difference attack is a simple example where 2 questions, each of which in isolation seems pretty harmless, when combined, are really, really focused on learning a sensitive piece of information about one individual. So it's a way of constructing 2 very closely related questions whose difference in the answers is something about a specific individual. So hopefully what this example drives home is just that it's very tricky to define when is a query giving aggregate information versus when a query or a statistic is giving individual specific information. It depends not only on the query itself, but on what queries are being asked with it, and what information the attacker or data analyst has used to kind of target and specialize the query to you. So I should say this example might seem almost trivial. It's very contrived, but it's actually a useful example to keep in mind as a test case of lots of issues. So we might come back to it at various points. It's always a useful thing to think about when reasoning about privacy in this class. So that was a very simple example, but you might say, look, these questions look kind of suspicious. Maybe we can kind of detect when someone is engaging in this sort of behavior and trying to mount a differencing attack. at the very least, maybe a differencing attack is only relevant if we let the user specify the questions. What if we are trying to produce some summary statistics of a data set for the public? We're not going to choose these weird combinations of questions. Maybe everything's okay. So what we're going to do next is an example inspired by the Census, which is an organization that collects demographic information on the entire US population. And we're going to see how even kind of benign, natural-looking statistics can lead to Reconstruction attacks that target individuals. So first of all, a little background for those who don't know. The United States Census Bureau is tasked with keeping an accurate count and collecting demographic information about the United States population. They have a constitutionally mandated role to count the individuals in the United States for purposes of electoral votes and congressional apportionment. And every 10 years, they do what's called the decennial census, where they collect, they essentially count the number of people in the US and collect information about their age, sex, race, where they live, what type of house they live in, and various other demographic information. And they make this data available for various research purposes, but federal law prohibits releasing the individual responses, which are called the microdata. So they cannot reveal what is on my census card. So instead, they release these tabulations, and they take various measures to make the tabulations private. So for the 2020 census, they've committed to using differential privacy, but in past censuses, they used a set of heuristics for trying to make sure that these counts don't reveal individual specific information. So for example, they're well aware that releasing small counts can be problematic. And so if you look at this table, you'll see a bunch of entries that have a D in parentheses, and these are cells that were suppressed where the count was small. I think in this case, the example is smaller than 3, so 0, 1, or 2. So they release tables like this with a number of statistics. So this is an example from a paper by Simpson Garfinkel, John Abowd, and Christian Martindale, explaining Reconstruction attacks that were actually carried out on the US Census. This is a toy example, but it describes real attacks. So the rows in this table are statistics like the total population, and it shows that the total population is 7. The median age in that population is 30, and the mean age is 38. And you can see they've released these for a number of demographics, such as those who reported their sex as female, and those who reported their race as Black or African American, those who are 64 years or over. So they have a number of these counts for subsets of the populations. So let's think about what we can learn from this table of counts. And the main idea is that each of these rows of this table gives us some constraints on the underlying microdata, and we can make inferences about the underlying microdata by trying to play around with what is consistent with those constraints. So, for example, let's kind of highlight for a second the statistic 2b, which is the row pertaining to males in the data set. So the first thing we know from this is that there are 3 males in the data set. And let's see if we can recover some information about what the age of all 3 of the males is. So first of all, there are 3 ages. So 3 males, ages A, B, and C. And let's suppose, there's no way of kind of ordering the males. So let's just assume that A is the age of the youngest male, B is the age of the middle one, and C is the oldest. Okay, so I'll just decide that A, B, and C are going to be sorted. And I also know something about these numbers, right? So first of all, I know that have some reasonable guess, let's say, that none of these people are older than 125, which I'm basing on the fact that, according to Wikipedia, the oldest confirmed age of a human is 122, and I'll be a little generous and go up to 125. And of course, I know that no person is younger than 0, but for purposes of this, I'm going to assume that nobody is younger than 1 year old. And I'm going to do that because that's what they did in their paper. And so it'll just help me be consistent with the next table that I'm going to show. Nothing would really fundamentally change about the example if we removed this. So we know that there's 3 numbers, A, B, and C, and they're between 1 and 125. And what else do we know? We know that the median age is 30. So if the median is 30, that means that B equals 30, because the median of 3 numbers is precisely the middle of those 3 numbers, which we've called B. So we know that one of the people in this data set is a male whose age is exactly 30. So at this point, we can sort of take stock. We know that A is at most 30. And we know that B is equal to 30. And we know that C is at least 30. And we also know that the mean, which is A plus B plus C over 3, is equal to 44. That's what this entry tells us. So we can also get some information about A and C. We know that A plus C plus 30 all over 3 is 44. And that tells us that A plus C is equal to 3 times 34, if I'm doing my algebra right, which is 102. All right, so the remaining 2 numbers have to add up to 102, and they A has to be smaller than 30, and C has to be bigger than 30. So we can just enumerate all the possible combinations that are consistent. So very cleverly, I've hid a table in which that information is presented. So these are all 21 possible choices for A, B, and C that are consistent with the table. All right, so you can look at this and say, all right, is this really so bad? So first of all, we've learned something. So even though we know that humans can occasionally live to be older than 101, we've learned that no male in this data set is older than 101. And that's about all we've learned. So, we've learned that someone is 30, the other person is younger than 30, and the last person is younger than 102. But if you think about, what we've done, we've reduced a space of something bigger than 300,000 possible choices of A, B, and C that are between 1 and 125, and we've reduced it down to just 21 possible arrangements. And we did that with just one statistic, so just with statistic 2b. So it's not hard to extrapolate from here and figure out that if we add more information to the table, if we start taking into account, other things about the table, then we are going to quickly pin down exact microdata from the table. So to that end, let me give you a specific example to work through as an exercise. So let me do a little iPad arranging. So let's suppose I wanted to be a little more ambitious with my data release, and I decided not to suppress the Black or African American male statistic. So I decided to tell you that there are 2 Black or African American males in this data set, and their mean age is 28. So now what I'll ask is statistic 2b plus 4b enough to recover ABC? Or are there 2 or more choices consistent? All right, so that's the question I'd like to ask. So now that I've made the table a little more specific, does it give you enough to recover the ages of all 3 of the males in the data set, or does it not? So at this point, you could pause the video if you're following along at home and think about the question for a bit, or if you want to come back to it later, you can just go on. So, oops, little first lecture jitters there. So let's talk for a minute about sort of Reconstruction as an abstract concept. So what's a kind of general way of expressing what happened? Well, we had some data set X. This is the underlying microdata. Okay, so we had some data set X that was the underlying microdata. This is the census forms that the census collects, saying everyone's race, sex, and age. And now we're going to release a bunch of statistics. So we have some set of statistics F1 through Fk that we're going to evaluate on the data set. So these are the statistics. Sometimes I'll call them queries, and sometimes I might call them counts. These are kind of interchangeable terms in the context we're studying, but depending on what type of statistics we're releasing, different words apply. So it's a good time to just mention that we'll sometimes use these terms interchangeably. And what we get are answers that are possibly noisy. Okay, so what we get is a list of answers saying A1 is F1 of X, and this may be approximate. It's possible that we're not getting the exact answer. Maybe if the count in question is too small, we don't see the exact count, we just see that it's smaller than 5. Okay, so we get a whole bunch of these, K of them specifically. And this is kind of a general version of the table we saw on the last slide. And what these are constraints, right? These tell us that X cannot be anything. It has to be a data set for which A1 is approximately F1 of X, A2 is approximately F2 of X, and so on and so forth. So these constraints that narrow down the choices for X. Okay, so for example, we saw that after looking at one statistic in the data set, the only consistent choices for X were ones where the there were 3 males, and their ages were A, B, and C, where B is 30, and A and C had some number of possibilities. And then more statistics narrowed down the set of X's further. So kind of what is Reconstruction? The sort of Reconstruction problem is given constraints of the form fi of x is approximately equal to ai for a whole bunch of different queries fi and answers ai. Find a data set x tilde that is consistent with the constraints. Okay, so this is what I'm calling the Reconstruction problem. It's a very general problem as I've stated it, because I haven't really told you anything about what types of statistics f represents, how much noise there is in the statistics, and so it's hard to say anything about how to solve it. But the kind of central thesis of Reconstruction attacks is that if I give you enough constraints, and they are specific enough, meaning that the accuracy of the answers, the approximation is fine enough, then it should be possible to reconstruct x either exactly or very close. So if we give you enough constraints, there should be only one consistent x, or only a small number of consistent x's. And even if there's not enough information to reconstruct all of x, often just finding anything that's consistent will give you some information. So in our previous example, we didn't reconstruct all of x, we just reconstructed the part of x corresponding to 3 males in the data set, and we didn't learn their ages exactly. We learned that one of them has an age of 30, but the other 2 had certain ranges for their age. So Reconstruction can give us either x exactly, or it can give us x approximately, or it can give us some part of x. So what we're going to see in the rest of this lecture and the next lecture are specific settings where where certain types of statistics guarantee that we can recover x nearly exactly. And before I go on to talk about that, I want to make one additional comment, which is that this problem is algorithmically very complex because we haven't really specified anything about it. But in its most general form, this is called a constraint satisfaction problem. And for many different applications, this will be an NP-hard problem. So this will be a problem that we can't solve in complete generality in polynomial time. But even in those cases, in practice, we can often expect to solve reconstruction problems using tools like satisfiability solvers or integer programming solvers. So what we'll see in the next lecture is also that there are 2 aspects to reconstruction. There's a kind of statistical aspect, which asks when are these constraints enough to tell me useful information about x? And then there's an algorithmic problem, which is how do I extract, how do I actually do the reconstruction and recover x? And sometimes there's an interesting interplay between those 2 things. Sometimes the algorithmic problem is sort of trivial. Sometimes it's kind of NP-hard in general. So we'll talk a little bit about both the statistical and the algorithmic aspects of it.